Hi everyone, I'm an structural engineer working in the UK with over a decade of experience now, and I passed my IStructE exam a few years ago. I'll be going through the question for the ex-pass paper for February 2023. This part of the video, this is going to be section 2C, and it's just a continuation of the previous video where I was working out the load takedown. Now I'm working out or designing one of the primary structural elements, which is going to be the roof truss. Now we're going to start designing our first primary structural element, which is going to be the truss. So I'll say roof truss. First we need to design, well, we decided that it was going to be a Pratt truss. But with a slope to provide a drainage for the roof. We know that, well, I'll redraw it here because we're far ahead now. Our roof will then be something like this. Right? I think this is the Pratt one. Double check later if it's not right. And we know this is 1.4 from the previous videos, and this can be up to 2 meters higher. Okay. We know that the truss spacing, it's approximately 12 meters, which is a column spacing, and the span, the worst case scenario for the span was the cantilever. The reason is because the effective length of the cantilever, even though the cantilever span is 8 meters, and then I think the maximum span in between was 14 meters, the cantilever length, the effective length of it is actually double the actual span. So instead of being 8 meters, the effective length would be 16 meters. But of course, for our calculations, we will use the 8 meter value, unless we need to use the effective length, of course. So we need to calculate what's the load applied on the roof truss. And for that, let's just draw it here. In the cantilever part, which is going to be the worst case scenario, we will have the load applied on the roof. We will also have, I think it was yellow that we used, the load applied on the conference hall. I think that'll be it. It's weight. So let's see if we then say, okay, our spacing is 12 meters. And the roof load, which was in purple, I think, would be for SLS. Let's come back and check. 1.6, and for ULS 2.25. Okay, it's 1.6 times 12. And ULS 2.25 times 12. This will be our UDL applied on each truss. So 1.6 times 12, 19.2. 2.25 times 12, 27. This will be in kilonewtons per meter. And then if we go to, it's not the roof, now is the level 4 conference hall level. And we go back to our calculating our UDL. And we start SLS. Well, what's the value? 9.25 and 13.24. 13.24 is 5. ULS is 9.25 times 12. 12 times 12. And this is also in kilonewtons per meter. Kilonewtons per meter. 111. 111. 13.2 times 12. 158.4. Okay. I think one thing that I didn't mention here that you need to make sure that you're right in your exam is to explain why we're taking the cantilever. I kind of like explained it in here, but I didn't write it, and you need to make sure that everything you assume is written. So what I'll write is just by inspection, the cantilever of the of the truss is the worst case scenario for the roof truss, as the cantilever length is 8 meters and the effective length factor is 2 for cantilever, plus the load we know there's not going to be the part in the lower roof area because the load is much higher in the conference hall area, plus the load in I'll continue here, plus the load in the conference hall area is much higher than other areas of the roof or level 4 and level 4. Okay. See. Okay, now we say then our roof, or a simplified diagram, for roof is going to be cantilever beam, which is 8 meters long, with right. Now the way that this load is applied, I was just thinking, the one on the roof is going to be a UDL. However, the one in yellow is actually, so I'll need to write that the load from the conference hall area is transferred by hangers. In tension. So it will be the equivalent of point loads. But for simplicity, because the point loads are at closed centers, then we're going to assume distributed as UDL. Okay, so we also have the yellow UDL. Carry on. And we go then at the sign moment, MD, and A descent shear. MD will be equal to your load times, which your load is 158, and then right, for there will be two MDs, right? MD for SLS and the sign moment ULS. For SLS, it's going to be 158.4 plus 19.2. 8.4 plus 19.2 times 8 meters squared divided by 2, I think, right? So this times the length and then divided by 2, yes. And that's equal to, let's see, what were the values? Oh, sorry, I took 158.4. No, it shouldn't be 158.4. It should be 111 because it's SLS. So it's 111 times 19.2 plus 19.2 times 8 times 8 divided by 2. And this is 4,166 kilonewtons per meter. And we then go the MDULS, which is 158.4 plus 27. 158.4 plus 27 times 8 meter square divided by 2 plus 27 times 8 square divided by 2. This gives us a moment of 5,932.8 kilonewtons per meter. Okay, and here is the, in my opinion, the most important part in the calculations, and is showing that you understand then how you're going to design this truss. And what is actually the most important part of the truss is the truss will resist the bending moment primarily by the top and bottom chords in axial forces. For the cantilever case, the top chord will be in tension and bottom chord in compression. Okay, and then we show it by making a small graph. All right. We know this is going to be incline, but this part is 1.4. and we show the top one. It's going to be in tension. On the bottom one, compression. With the diagonal, also in tension. And we have our UDL applied. Well, we got the forces here, so force F, F, and our UDL apply on the top UDL. Okay. Once we know that, and we explain that this is basically how it is behaving, and that the bending moment will be resisted by, I didn't draw the bending moment. Bending moment will be resisted by the top and bottom chords. Then we can start doing and going with the actual calculations of the steel truss. So we go and we say, okay, steel truss properties. It's going to be steel Fy. Now, this is why it's so important to have your template. Like right now I have my template next to me, and it's not going to be the exact same calculation of the templates that I have, but I know how to structure it now. So I know the layout of my calculations, how it will look like, and then I just go right straight away, Fy, what's the depth of my truss. I know the trusses, steel trusses tend to be a lot that I use in this type of designs, especially when there's such a long spans. So I know that this calculation is essential for me, that I bring it to the exam, or that I brought it to the exam with the template. So now we go the lateral restraint spacing. That's 1.6. Okay, now I'll show what this 1.6 is. We know that this design moment are ULS 5932. So 5932, and SLS 4166. Okay, 4166. Okay, so okay, what I mean by this lateral restraint spacing is that your beam is going to be 8 meters long. If you divide 8 meters by 5 equal sections, then 1, 2, 3, 4, 5. Each of them is going to display 1.6 meters, and this is 1.4. Again, this goes like this. It's not really horizontal. Is like this. This is 8 meters though, and this is 1.6. So I got the lateral restraint for my top and bottom chords with all the elements that are going to be in compression, and then I'll be checking that they're okay on the buckling. Then it's 1.6 meters. Now my horizontal force, FH, which is going to be the couple of forces from my bending moment, it's going to be well, it actually depends if it's an SLS or UDA or ULS. Let's say ULS. Then I go 5,932 divided by 1.4. Well, it's 1.4 here, but it's actually bigger here, where the maximum moment happens. So it's not going to be 1.4. Let's calculate what's the maximum that I can use. So I know that this is 1.4, and let me see. Okay, and this can be up to 3 meters. I think is what they say in the question. Come on. 3 meters. Okay, so I got this triangle, But this is when it's measured to the middle of the building, which is 8 meters of cantilever, middle of the building, plus 14 meters. Okay, so basically over 14 plus 8 meters, there'll be a decrease. I'm just doing a linear interpolation between these two to try to find out what my depth would be of my truss at this point, which is where it starts the cantilever. I don't think it's very clear here. Let's see. This is my building. I'm going to make it in pink. And we got the truss that will come like this. And then these are the two edge columns. Then there's two more columns here and the other one. But basically, this is the middle of the building, which is symmetrical. Okay, I'll make it simpler again. I got all the information right now and the moment and everything for the point of the cantilever of my truss. And what I want to now calculate is what's the height of my truss. I know there's 1.4 here. What's the actual height at this point, which is about 8 meters. Okay, so I'm doing a linear interpolation. It's 14 plus 8. Then there's a difference of 1.6 meters between 3 meters and 1.6 meters. So over 14 meters, which is this, 14 meters. What's the difference there? And this value is equal to 14 times 1.6 divided by 14 plus 8. It's 1.018. So this value is about 1 meter. So that means that the depth, or the height, let's call it, of my truss at that point is 2.4 meters. So if I come back here, this is 2.4, and my force is actually 5932 divided by 2.4. So my horizontal force is 2,472. Okay. Now I got my design force, and I write, it's 2,472 kilonewtons, and then we write both top and bottom chords will be subject to this load, one in tension and the other one in compression. The worst case scenario is the compression because of buckling failure. Okay, so we check the compressive resistance of bottom chord. Right, so if we take 25489 UCs, I just why did I take this one? I went to the blue book that I have, and then I just worked out what's size that will comfortably pass or resist this force over the 1.6 meter effective length of my bottom chord. But now I have to do the calculations to prove it, and now is take that one. The area of this one is 113 square centimeters. The critical length, as I say, is 1.6 meters. The inertia, not the inertia. I'll need the inertia, but I'm following my template, so the radius of duration is 6.55 centimeters, and my inertia now is 14300. All of this from the blue book, yeah? Now, what's the resistance to actual buckling then? My NRB is going to be the reduction factor because of buckling times the area times Fy. And to calculate the reduction factor because of buckling, then I need a lambda. The reduction factor will be dependent on my lambda 1. Lambda 1 would be equal to 19.3 times the epsilon. The epsilon would be equal to the square root of 235 divided by 355, 0.813. So my lambda 1 is equal to, well, this times this, and that's 76.34. Okay, and now I calculate my lambda, which is 1.6 meters divided by the radius of duration, which was 6.55, and then that times -2 because it's in centimeters. So lambda equal 1.6 and 6.5, 6.55, and then 76. And this is equal to 1.6 divided by 6.55, 10 divided by 76. This is 0.32. So this is a process of how you calculate the reduction value for buckling. That is in the IStructE guidance for the Eurocode 3 or even in the Eurocode 3. So it's just to calculate the buckling resistance of the element on the compression. It looks like a lot of complicated, but it's always the same process, and it's quite simple once you know. So once you have this lambda, you just have to go to the buckling curve that is shown in figure 6.4 in the Eurocode 3. Because our height and the width of our profile is approximately 1, then the buckling curve that I'll use is B. So because from this figure, I'll take that, then my reduction factor for a lambda of 0.32, they calculated here, it's equal to 0.95. That means that my resistance to buckling, it will be equal to 0.95 times the area, which was 133. This is in centimeters, so times, okay, this is getting too big. Let me rewrite it. So buckling resistance will be equal to 0.95 times the area, which is 133 in meters now, times the yield strength of the steel, and this is equal to 4,485 kilonewtons, which is higher than the design load that we had previously, that is 2,472. kilonewtons. Therefore, okay. And basically, that's how you prove that the bending capacity of the truss will be acceptable under the loads. And there's one final check that I'll include and that I have in my template of the calculation, is the calculation of the deflection, because it also shows, what I understand, the first, that not only the ULS cases are the important ones, also you need to check for serviceability. So we check now, strong enough, we check serviceability. So we calculate the deflection, and the deflection, if we take a cross section of the truss, it looks something like this. We got this as our height, which is 2.4 meters, sorry. We calculated before. This will be our strong axis, YY. And to calculate the deflection, we need to work out what's the inertia of this section. So to calculate that, I'm going to use the parallel axis theorem. Okay, so I'm going to calculate the inertia of this whole element using the parallel axis theorem. You can check online how it is calculated if you haven't done it before. The inertia of the overall or composite element is going to be increased by the square root of each unit, and you'll see by looking at the formula, which is the inertia will be equals to 2 times the inertia of them, which we had before was 14330. Had it somewhere here. And then plus, this is the part that I was talking about, the area times this spacing, the h, which is 2.4 divided by 2 squared. And this value is going to be equal to 3.856. Okay, centimeters. And then using that value that we obtain for the inertia, we calculate the maximum deflection, which is going to be the SLS moment. This is an approximation of the deflection, and the SLS moment was 4166. 4166 divided by 10 times span, and I'll multiply by 2 because of the effective length, that is a cantilever, square divided by the E value of the steel, the elastic modulus, and that times the inertia that we just calculated, which is 3.85. I'm just going to put inertia, and the inertia we have it here. So 4166 divided by 10 times 8 times 2 squared divided by the elasticity modulus, or modulus of elasticity, and divided by 3.85. Right. Because everything else is in meters, need to change this to meters too. It's going to be 5.33. This is the calculations, waiting for the result of the calculations, waiting for the actual inertia to be divided by it. So this value 3.85 power times 10 to the power of 6 divided by 3.85. Is that right? In meters. No. Right, 3.85 times 10 to the power of 3, 38.5. So it will be 38.5 times 10 to the power of 3, 5 times this divided by this. It gave us the maximum deflection, the approximation of the maximum deflection. In meters, which is 0.014 meters. So 14 millimeters, which over a span of 8 meters is L over 570, which is the okay. And we have now finished the calculations of the roof steel truss, and because it's a long enough video, I'll leave it here, and then the next video I'll carry on with the calculations for the hanger and the bracing and the foundations.